and parametric and static analysis can also be done.
Muted.
Let me start my presentation on the today's webinar topic, that is on introduction of JMAG important functions. So basically, let me introduce JMAG. So JMAG is electromagnetic simulation technology for electric design and development software. So being developed by JSL Corporation in 1983. So we are the distributor in India, and also globally we distribute the software in Europe, America, and in India. So PWSIM is an Indian subsidiary company of. So let me talk about the solver. The solver feed is directly related to the model accuracy and reliability. So basically, finite element analysis comes down to solving very large matrices. JSON developed the advanced techniques to solve these matrices faster and produce more consistent results. So for example, we have a parallel computing options. So if you see this graph, the number of parallel processes and the speed of the y-axis. So for example, this is a just example of this solver. So basically, JMAG can support many number of cores. As of now, in the graph, it has been shown for only 128 cores. So for example, for 8 core, the speed up will be around 5 times. So for 16 core, it will be a 10 times. For 32 cores, it will be 20 times. So similarly, for 128 cores, it will be around 48 speed up. Okay, so this shows how the JSON developed the advanced techniques to solve these matrices faster and produce more consistent results with more accurate results. So high-speed processing and scalability are the two main goals of parallel processing. So JMAG supports both shared and distributed memory processing and can be incorporated the graphic processing unit into calculations. So JMAG supports shared processing, that is symmetric multi processors, and distributed memory, that is MPP, massive parallel processing, and also it can support the GPU to the GPU for the calculations faster. So from the desktop to cluster and cloud computing, JMAG parallelization technologies can be used in a wide range environment. So utilizing these characteristics can be characteristics means that the analysis with over 10 million elements as well as models with hundreds of thousands of elements into a design cycle. So we can solve thousands of mesh elements can be incorporated for this design to calculate by using this SMP, MPP, and GPU solver. So let me talk about each SMP, MPP, and GPU separately. So in this slide, I am going to explain about the symmetric multiple processing, that is SMP, multiple CPU, multiple core support in this. So this is the graph which shows the number of threads versus speed up for different rotating machines and electromagnetic devices. So we have solved for IPM, interior permanent magnet motor, SPM, induction motor, permanent magnet synchronous motor, alternator, and transformer. So for a given SMP, that is shared memory processing. So it can use up to 36 cores. 36 cores means like we define it as in PA2, parallel accelerator. So each PA2 will have 2 cores. Suppose 2 cores. So to avoid complete 36 cores, we need to have 18 PA2s. So with addition of each PA2, say for example, with addition of each PA2 up to 36 cores, the solver speed will be increasing as per the graph shown in this graph as for the 7 different machines. So the latest version of JMAG improves the convergence of ICCG and nonlinear calculations with respect to increasing the number of threads while increasing the speed up. So let me talk about the MPP, that is massive parallel processing. So JSOL developed the JMAG high parallel MPP solver with high parallelization to realize a high-speed computation via cluster system connected to multiple computers called nodes in a high-speed network. So the MPP can be MPP solver high parallelization to realize a high-speed computation. So through cluster system connected to a multiple computers called nodes. So each computer have more number of cores that can be utilized as per the MPP usage. Enables using multiple GPU as well as multiple CPU in a cluster, which achieves a high degree of parallelism in analysis and increases calculation speed as well. So we have an example how MPP performs using JMAG in a cluster connected to high-speed network. So we ran a transient response analysis for one period of electric angle for a large-scale 3D PM synchronous machine. So it has approximately 2.06 million elements. So only as a result, only 2.5 hours and 1 hour 45 minutes were necessary for 32 and 64 parallels respectively. So for example, for 32 MPP solver, it took 2.5 hours, and for 64 parallel, it took 1 hour and 45 minutes. So almost we have 45 minutes lesser compared to 32 cores. So they are 13 times and 20 times faster than conventional non-parallel computing. So these are the hardware specifications we used while solving this MPP solver. So we have Intel Xeon E52670 frequency of 2.6. The number of cores are 8, and number of processors are 2, that means nodes, and the memory 32 GB, and the nodes are 16, and the network are in band QDR. So this is the graph which shows the time in minutes and the number of processors. So we have used up to 64 for one. So it took 2000 minutes. For 8 core, it took just around 380 minutes. So for 16, around 200. For 32 and 64. So like this, the speed of the solver has been increasing with increasing the number. The speed of the solver will decreasing while increasing the number of processors. This is the example for IPM machines shown in the 3D model here. So coming to the GPU, so for a large-scale mesh model with millions of elements, a large proportion of the processing time is required for solution finding. So we have an example for GPU as well. So JMAG GPU solver employs a technology to accelerate such processing times using GPU. So this section shows the effectiveness of the analysis time reduction when using a GPU in comparison with using a shared memory CPU parallel solver. So how the GPU solver is effective compared to CPU and MPP solver will be showcasing in this presentation with an example. So the following figure shows analysis times when conducting two steps of a transient response line speed analysis on a 4-pole 24-slot embedded type PM motor model. So this model has approximately 2 million elements. Compared with the calculation time of a single core CPU, the anticipated calculation speed increases approximately 10 times when using only one GPU and approximately 14 times when using two GPUs. Okay, here is the example of this. So the y-axis shows the time in minutes, and the x-axis compares the number of CPU cores and the number of GPUs. So this is the hardware specification. So we have a CPU Intel Xeon X5670 and also GPU NVIDIA Tesla K40. So this is for a GPU and this is for a normal CPU. So we have the cores of 12, and in the GPU we have 2880, which is also called as one GPU. Say for example, the number of CPU cores. Say for example, for one core, it has took almost 650 minutes, and for two cores, it has took around 300 minutes. So for four cores, four PA2s, that means eight cores, it took almost 170, and for eight PA2s, it took almost 150. But compared to this CPU core, if you use the number of GPUs, that is one GPU, it is almost the time took for a solution will be around only 50 minutes, comparatively 650. So if you compare 650 to just 50, it is been reduced to 10 times. Almost it is 10 times faster than the normal CPU core. So similarly, for two GPUs, it is 14 times faster than the normal CPU core. So this is the calculations example for the GPU compared to SLP and MPP solver. So also we can use JMAG in cloud services. So we have a 3D model with a fine mesh for IPM machine with coil and modeling. So the cloud services are also effective for using MPP solvers for large scale model computations. So in addition, in the case of multi-case processing, it is possible to simultaneously achieve reductions in license cost and in secure computational resource by combining power simulation license. So JMAG provides power simulation license for the various solvers for the 2D transient static analysis access the power simulation license to calculate parallelly for solvers to reduce the license cost. Cloud services enables analysis work using sufficient computational anytime, anywhere. So the cloud services supported by JMAG are like the vendor Rescale Inc. and the cloud is multi-platform. Amazon Web Services, the cloud is Amazon AWS. So in the cloud also we have an example, an embedded type eMotor with 2.75 million elements and 1.35 million nodes is calculated with a massive parallel processing solver using Rescale platform to perform parallel calculations. Calculation speeds were improved using up to 256 parallel processing. So that means like we have solved 2.75 million and 1.35 million nodes is calculated with a MTP solver. So using Rescale platform in the cloud system. So in the cloud we have used up to 256 number of parallel processors and the speed up was increased to 40 times the normal CPU core. That means like 8 core. So apart from this solver, we have a good meshing technology in JMAG. So in JMAG we have an automatic mesh where the JMAG automatically grabs the air region and do a fine mesh to capture the magnetic circuit phenomena. So in the air region. So we have an adaptive mesh technology. JSON's unique development methods run high-speed adaptive analysis for rotating machines that are highly accurate. They can achieve speeds over 10 times faster than traditional methods. Using adaptive can achieve 10 times faster than the traditional methods of the machine technology, so which was developed in JMAG. So also we have a slide and rotating machine mesh for the rotating machine. So you can see for the axial gap motor. So we have a slide plane in the air region between the stator and rotor for the axial gap motor. So this kind of meshing technology can be used in the JMAG for the rotating machines. So also this is the motor case example. So here is the slide plane between the stator and rotor in the air region. So also we have a expanded slide mesh, that is extruded slide mesh. So where for the complex 3D models, we can avoid the more number of mesh elements creation using the extruded slide mesh, where the axial extrusion part can be defined as a extruded mesh to avoid the more number of mesh elements in the analysis. And that will avoid the simulation time compared to the normal semi-auto mesh or auto mesh. So also, JMI mesh modeling technique has another option called layered mesh. The detailed modeling for the lamination of the steel sheet has been shown in this example. So this is an example for the layered mesh for the layered laminated steel sheet meshes. So for example, if you see in this region, this thin lamination plate has been divided into so many layers to account the lamination eddy currents in the lamination sheet. So in this kind of an example, we can use this layered mesh to account the skin effect, eddy current penetration in the lamination steel in the soft material using this layered mesh technique. So also we have thin plate meshing technology used for the transformer tank. In this example, we have shown for the transformer tank, so where the eddy currents because of the Joule of calculation can be easily calculated with more accurate on this clamp, shield, and the other structural materials to calculate this eddy current distribution as well as the eddy current loss. That means the Joule loss. Generating mesh for an extremely thin plate model in the analysis space, such as shield or chassis play panel, is difficult using conventional mesh generation methods. So using JMAG, thin plate mesh features can be generated sufficiently large mesh in the plane direction based on the layers of mesh that is being generated in the sequence direction. So you can see in this example where the thin plate, the shield material can be taken in the large viewer angle. So where you can see the thin plate meshing has been generated in that area to calculate the eddy current loss. So also we have a skin depth meshing. So where Skin function can be used to generate a layered mesh of a specified thickness on the surface space of a certain part. Say, for example, the eddy current has been, in this example, we have shown for the Clapon alternator, the eddy current vector distribution on the surface of the Clapon. Say, for example, on the surface of the claw, so the eddy currents are penetrated inside the surface on the claw. So to account that, so we can define the skin depth. Skin depth in a mesh, and we can do a layered mesh on the surface into that thickness, and we can accurately express the offset in magnetic flux distribution caused by the skin effect. And secondly, you can generate a mesh capable of evaluating the effect of eddy. So here the applied skin depth is shown in this picture, and here without skin depth not applied. So you can see the distribution on the eddy current difference between these two pictures. The eddy current vectors are disordered in this case without skin depth, and the eddy current distribution is ordered with applied skin depth option. So these are the two difference why the skin depth mesh is needed in the simulation. So also the mesh generation technique has been improved in the latest version of the JMAG. So earlier the number of parts, for example, in the x-axis we have defined the number of parts. So and the y-axis the mesh generation time in minutes. So the conventional one it is taking almost 180 minutes to generate mesh for 150 parts. But in the new mesh technology developed in the latest version by JSL Corporation Japan, so the mesh generation time is reduced to almost 30 minutes. So it is very faster to do a mesh for 150 parts. The amount of processing required will increase proportionately to the number of parts. By applying parallel processing, so measure processing speed increases and mesh generation time is also reduced considerably. In this picture, we have shown in this compared to conventional one and the newer measure. So after mesh, we have a technology to create a coil in geometry for a complex model. So for example, firstly, I will show you how to create a wire by simply typing a few parameters in the slot by using wire template options. So for example, in the wire template options for the 2D model, we can define the area. I mean, area means the slot area, and we can define the slot fill factor, and we can define the wire thickness, the wire insulation, everything. So the automatically JMAG can create a wire in the slot based on the defined parameter, based on the defined parameters in the wire template window. So why we should use this wire template option? Because the AC to account the skin effect and proximity effect and the leakage flux and the eddy currents in the conductor. So this type of analysis we can perform by using this wires defined in the motor analysis. So the second one is we have a detailed modeling of coil and geometry. Detailed modeling of coil and geometry where the end winding can be defined by using the coil and template option. So in JMAG geometry calculator, we have two options. So one is to create a wire template, and the second is to create a coil end winding to accurately calculate the end winding leakage inductance. So for a square wire coils and higher motor speeds, so as I said, the AC losses to be ignored as a loss factor. But the coil losses are caused by the skin effect and proximity effect due to frequency. So wire geometry and wire placement as well as by current density distribution concentrated in wires arising from leakage flux that links with coil ends can be calculated by this first type of analysis, that is the with wires we can analyze with proximity losses and the skin effect. So with the 3D analysis by creating end winding geometry, we can create the leakage flux. I mean, we can calculate the end winding leakage flux that links to the coil. So apart from the creating coil and geometry, we have a material modeling technology in JMAG where providing highly reliable analysis systems, safely implementing realistic physical mechanisms as best as possible, because the material modeling is used to calculate the magnetic performance of the electric devices. So the material modeling is very important, as JMAG is developing for incorporating the material data to JMAG material database. So JS will continue to develop modeling technology for JMAG to provide the best model at each stage. So from micro behavior inside material to multi-physics phenomena and control systems. So for the material modeling, so we can create a magnetization material and you can import the user's magnetization material option. So we have a temperature dependent material in thermal properties and we can account the temperature dependency of the BH curve. So we can use error of calibration for degradation and the modeling accounting for stress. We can also create a material accounting for the stress dependent BH curve. So as I said, you can see in the error loss density distribution. So in this figure, you can see the iron loss density distribution. The left is without degradation and the right is degradation. So on the teeth, with because of the higher degradation of the lamination, the iron loss effect can be calculated by using the loss model function in JMAG. So here is the data table where we can input the temperature dependent thermal conductivity versus temperature. So this is the data we input it in the point sequence. So the x-axis, I mean the temperature was in degrees centigrade and thermal conductivity we can incorporate here to account the magnetic behavior of the electric device. So here this is an example of the stress dependent material properties for 35A360 material. And apart from that, we have a JMA Express for motor design, where you can quickly import the 2D model of the model of various type of machines, induction machines, permanent magnet machines, SRM, and other sorry, and other type of motors. So once we define the geometry, the material, drive condition, and the winding parameters, we can quickly calculate the performance characteristics like torque, speed, efficiency, losses, power, and etc. So these are the various templates available in the JMAG Express motor design tool, where you can choose the combination of stator and rotor, and you can define your geometry spec and the characteristics quickly in 1 minute by using JMAG Express motor design tool. So coming to the modeling, we have a JMAG designer where you can perform 2D, 3D simulation using technology. So there is a dedicated shape modeler made for JMAG model creation. That means 2D and 3D shape modeling can easily be performed with a CAD link feeling. So as I said, we can create a 2D and 3D sketches using JMAG CAD editor, and and that model can be incorporated. Sorry, and that model can be directly imported to JMAG designer SPA GA, and you can perform the analysis. Also, we can import the third-party CAD files directly from the in any of the formats, say for example, CAD format, CATIA, SolidWorks, and GUI, the other third-party CAD formats can be directly imported to JMAG Designer to perform the analysis. So we have a template for various applications. As I said, in JMAG Designer, we have a template for motors, transformers, and also for wires and conduits. So we can do a section analysis in JMAG Designer, where if you have a 3D analysis model, you can take a section and you can perform a 2D analysis, and you can see the result. So both 2D can be converted into a 3D and 3D can be converted into a 2D by using section analysis. So we have another key function like multislice method, where for a 3D model where we have a skew effect, so that can be simulated by using multislice method with faster time. So for example, enabled a high-speed calculation for 2D model incorporating 3D effect. I mean, recalculation by the multislice method is possible based on the existing 2D data. So we can define the rotating angle in degree, and we can select the sections like 5 sections, 7 sections axially, and we can define the skew angle and we can perform the analysis. So for example, this line is a 2D where you have a where you do not have a smooth curve. So for a 3D section, so we have a smooth torque ripple. and but the same 3D graph can be created. We can calculate by using the multi-slice condition, where you will be having a same curve as like in the 3D section by defining 5 sections, 7 sections depending on the model length. So we can define this section for the screw, and you can define the screw angle, and you can get the same type of torque curve as like a 3D analysis. So in this we can achieve the we can get the results in a faster time compared to 3D simulations. So that is the benefit of this multi-slice method. So also we have accessibility option where we can in JMAG simple rotation and translation motion can also used without any restrictions. So using without any CAD modifications, we can define the movement. The x-axis of the stator motor can be displayed by using the accessibility condition given itself. So we can offset the x-axis and y-axis, and also in the z-axis. So that means that is what we call as the eccentricity. So apart from that, for the induction motor, we have a TPEC, that is time periodic explicit error correction method. So where you have a long transient curve, so where you can settle the transient curve into a steady state in a shorter time period, in a shorter time, a shorter number of steps. So it shortens the transient period that occurs in a transient analysis and forces the model into steady state operation in fewer minutes than if the model were allowed to achieve steady state operation on its own. So using this CPEC, because of the induction machine, I mean the induction machine, because of the eddy current phenomena, so the time taken for the steady to get the steady state curve will be more. To avoid that, using this CPEC, correcting the frequency and the number of cycles, we can correct the previous calculation, and we can achieve the results in a shorter time and get the steady state curve. That is the benefit of this TPEC function in JMAG designer solver. So we have multi-objective optimization technology. So where JMAG supports the optimization by using we have various optimization techniques. That is genetic algorithm, multi-objective optimization, MATLAB global. Using these three methods, we can achieve the best optimum design by defining the objective parameters and design constraints. So this is an example of the multi-objective optimization technology. The multi-objective optimization function using genetic algorithm is a new addition to the optimization calculation option in JMAG. So design exploration can be carried out without error, even for design phase with multimodality, because GA retains several results from which narrowing down of the results can occur for the optimization. This is an example where the multi-objective optimization is performed on an IPM motor to maximize the torque and minimize the torque ripple. So the x-axis defines the average torque in Newton meter, and the y-axis defines the torque ripple. So where you have a various results for the various design topology of the rotor configuration. So for example, the left hand side shows the initial design, and the right hand side shows the optimized design. Okay, so for these various shapes, for a given defined objective condition, that is increase the average torque and minimize the torque ripple. So we can select the best in the multi-objective optimization, and we can select the best operating point in a Pareto curve, uh, Pareto curve of the so many cases which is generated during the calculation. In this way, we can optimize various topology and various design parameters we can optimize by using this JMAG optimization function. In addition to that, we have a topology optimization where we can select the area, and we can select the best case and the best shape of the magnetic device, I mean, the best design can be selected by using this topology optimization. So the requirement of the motor designs are getting more advanced, satisfying torque ripple, line voltage limit, stress of core, as well as maximizing the torque at low and high speed. So in order to achieve these, so we can go with the topology optimization, which can yield effective results. So JMAG designer supports both parameter optimization and topology optimization. Topology optimization can be performed using JMAG model used in the design, and it will produce a design proposal with a new magnetic circuit. In this case, this is the evaluation space. It's an iron sheet and this is an air. This is just an example of the shield design area. This is a coil. Because of the coil, current in the coil, it will produce a magnetic flux in the iron part, and you can see the magnetic flux density distribution in the iron region. In the iron region, it is more, and in the air, it is very less. So based on this, so this is an area. This area has been modified in this shape. Later, you can fine tune that area to get the best design. So this is just a small example how the topology optimization will function in JMAG designer. So that's all my presentation. Sorry. I have another slide where we can create a efficiency map accounting the iron loss and the controlling effect. So it is important to take into account the carrier hormone and hazy copper loss in order to accurately calculate the efficiency of the rotating machine performing variable speed operation. So with motor, with controller and without controller, we have various efficiency map can be generated. So without controller, we are not controller loss effect and the harmonic loss effect. So those are ignored in the motor efficiency map. So in order to account that, magnetic field analysis for the motor and circuit analysis are performed using strong coupling. This makes it possible to fully consider the mutual interface between the motor and the inverter controller. So this is the PWM inverter and this is the motor. So the current vector controller will be adopted in the control circuit. So it's a voltage command. Okay. So accounting these by using a strong coupler between the JMAG and the other third-party software like MATLAB. So we can create an efficiency map using plant model. Obtain the current vector at maximum efficiency. Pick up operating points to be calculated. Set the speed and current vector command. Coupling analysis with control and circuit. So update the efficiency map considering the inverter carrier components and the AC losses. So this is the procedure how we update these losses into the efficiency map, accounting the inverter losses and the harmonics effect as well in the efficiency map. So here we have a motor drive development with the JMAG MATLAB simulating complete. So this is a example where we can update the JMAG FEA model into the circuit simulation software. Sorry, circuit simulation software like MATLAB Simulink, and you can do a closed loop simulation. Together with MathWorks, the company that develops MATLAB Simulink, JMAG strongly supports model-based development, which is utilizing for developing motor, drive, and HEV. Also, the motor drive system exhibits both high responsiveness and an excellent electric efficiency, which requires high power motors and advanced control algorithms. So, together with coupled analysis using JMAG, so we can achieve we can design the control circuit using virtual motor design data taken from JMAG API software. So that completes my presentation. If you have any questions, please let me know. So you can unmute your mic and you can ask me if you have any questions, please. You can define your question in the chat box. Also, I'm going to type my email ID. You can reply with your queries to this email ID. I will answer those queries. Okay. So,
Hello, sir.
yeah,
Hello,
please.
sir. Sir,
Yes. Yes.
good afternoon, sir. It was a nice presentation. We got
Yes.
insight about JMAG and as well now how to perform low load and loading performance analysis in this mode.
Sorry, your voice is breaking. Can you repeat you again your
How to
question?
perform, sir, how to perform low load and loading performance analysis for a beam DC motor?
For BLDC motor.
Yes, sir. Which parameters is most important, which we want to
Okay.
tune?
Okay. So, for example, in the BLDC motor, the no load
Yes,
means
sir.
like the current in the winding is zero. Am I right?
What, sir? Yes, sir.
I mean, in the no load, the current in the winding is zero. So by supplying zero current to the winding, we can and by defining the speed, we can get the no load characteristics like the KMS and the other parameters, no load magnetic flux. By defining
Okay,
the zero amp
okay,
to
sir.
the winding, we can perform the no load
Okay.
analysis. So to perform
So
the
if we
load
give zero,
analysis,
okay, sir.
yeah,
Yes, sir.
yeah, by defining the proper load current to the three-phase winding, so we can perform the loading characteristics to get the proper torque for a given speed.
Hello, sir.
Is it clear?
Sir, is it can it possible to perform a variable loading conditions?
Sorry,
Variable loading conditions for the beam DC motor and take characteristics performance.
I did not understand the first two words.
Sir, actually, I want to do a variable loading conditions. For example, for a particular time, some other extra load will be acting. Like that, I
Yeah.
should do a variable loading analysis.
Yes. Of course. In JMAG solver settings, we can define the time step, okay, for a given time in time, and we can change that end time to another time to define the other load condition. So we can do it actually. We can
Okay.
define
So
variable load
I will
condition
take
for a different time.
I will take a help from this regard, sir, later.
Sure. I have an example. We have done for
Okay.
demagnetization analysis for an APM, where
Okay, sir.
initially we have done it for no load condition, and then we have applied the load, and then we have removed the load. So in the single
Okay.
step analysis, I mean in the same analysis, we have done three loading conditions. One is no load, and then load, and then no load during the
Okay.
demagnetization analysis for APM machine.
Okay. Demagnetization analysis.
Yes.
Thank you, sir. Thank you for your support, sir. Thank you so much.
Because in demagnetization, so before no load condition, after loading condition, so how the magnet behaves because of the high loading
Okay.
current.
Okay.
So in order to get that information, so in the same analysis, so we applied the load and we removed the load to see the torque performance because of the
Okay. Okay, sir. Okay. Thank you, sir.
any question.
So Siddesh, I think that is it.
We can end the webinar, right?
Yeah. I think that is it. Over. There are no more queries in that regard. So actually, one person, Ms. Aishwarya, she has asked a question regarding. Can you explain the co-simulation of MATLAB with JMAG with an example?
Co-simulation. Okay.
Yeah. If you could do that, then
Okay,
we can. We can wind up the session with that.
We can do that actually. Maybe we can have a separate session for that, because it takes some time to to gather the data to a single common folder. So, and also I did not check whether my MATLAB is working or not. So we can take a separate session with Aishwarya, and we can show the demo of MATLAB and JMAG co-simulation. Is it okay, Rajiv?
Yeah, sir. Okay, one more query has come in. It's from one madam Padmini from SRMIST. She's asked, could you please elaborate on multi-objective optimization?
Okay. I will just I'm just opening the presentation. Yeah. So can you see my screen now?
Yeah, you can go ahead. Yeah.
Yeah. I'm just loading the model. Okay. So we have performed the optimization for this model. Before that, what it is, I'm restoring the CAD link. Okay. So in this case, we are our main objective is to increase the maximum torque and rippleness in the torque. Okay. So for that, what we did is we have constrained certain parameters. Say for example, you can see here the distance between the center of the magnet and the edge. Okay. And also, this is one part. And the second constraint is on the rotor. You can see this distance, the center distance, and the magnet width, and the magnet from the top. I mean the distance of the magnet from the top on the surface of the rotor, outer rotor, and width. Okay. So these are the four different design constraints we have selected for the optimization to vary by during the creation of the cases. Okay, so when we run these cases, we have an optimization dialog box where for a given defined design variables, so we can define the minimum and maximum values. So it means the minimum can be 0 and the maximum can be anything based on the design constraints. So for the width, we have defined it should vary from minimum 8 to maximum 11. And for the height, it can vary from minimum 1 to maximum 4. And similarly, the distance between the outer surface of the rotor to the magnet center, so it can be varied from 1 to 4. So based on this minimum and maximum of the design variables, so we define the objective function. That means like the maximum torque can be maximized and the minimum torque ripple can be minimized. So these are the objective conditions we defined for these two outputs. So initial cases has been selected, and the number of generations can be 2, and the population sizes can be 10. It is the initial cases to generate. So we can define as like we want. As of now, I'm just defining it to create 20 cases. So the first condition, the first case is for the base simulation, and the next 20 cases are the new cases which will be creating by using the design variables. So in this case, each generation will create 10 population cells. So total number of generations are 2. So 10 into 2 will be 20 cases. So these are the output. And once you check and click OK, the simulation will run, and that will be the response data will be generated like this. This is for the maximum coverage in the case. So total we are defining it for 16 cases, and we have a maximum torque for the various topology. So this is for case 1, we got 2.63, for case 2, 2.43, for case 10, we got 1.81. Like this, we can see each case will have different rotor structure. This is second. You can see the magnet width and the rotor topology is getting varied. Like this. Based on the constraint condition and the defined minimum and maximum for the constraint parameter, so optimization engine will vary this topology, and each topology the case will be run and the results will be out. Like this, total 21 cases has been run, and the result has been compared in the case. These are the results for various cases. Any questions? This is for the first case. So Pareto curve can also be generated by using this response curve function in this. So the Pareto curve will be generated like this. This is y-axis will be torque ripple, x-axis will be average torque. So like this, we can select any of the design parameter to vary, and we can define any of the objective condition to achieve, and we can run the simulations for so many cases, and we can get the best result. It will be out from the optimization after ending this simulation. Is it okay? Hello? Pradeep?
I think that's it. We don't have any more queries, so I think we can wind up the session for the day.
Okay. So thank you all for joining this webinar. So see you soon again with the new topic of the webinar in the upcoming week. So we'll keep on posting these webinars during this lockdown period online. So you can contact me with this email ID if you have more queries and to inquire about the software. Thank you. Thank you all. Bye.